Hello. In this video, I'm going to talk about linear inequalities and compound inequalities and their graphs in two-space. So, in a previous video, I explained the graphs of constant equations like x equals 7.2, which is this vertical line right here that goes through 7.2 comma 1, 7.2 comma 2, etc. Now what I'm going to do is I'm going to look at the graph of x is less than 7.2. So x is less than 7.2. Well, what points have an x value less than 7.2? All these points over here. And I'm going to turn it on, and there you go. Look, all these purple points, all the purple points have an x value less than 7.2. So all these red values right here, notice they all have an x less than 7.2. And so they're all very easily on this left side of the boundary line. These black points, on the other hand, notice their x value is greater than 7.2, which is why they are not solutions to this inequality. They are not in the solution set because their x values are greater than 7.2. Okay, now let me take these off and move them up here. Okay, so we're looking at the graph of x is less than 7.2, but what does the graph of x is greater than 7.2 look like? Well, it looks like that. It's all points who have x values greater than 7.2. What is the difference between x is greater than 7.2 and x is greater than or equal to 7.2? Well, the only difference is that the points where x is equal to 7.2 are now solutions. You'll notice that x is greater than 7.2 has a dashed boundary line to indicate that points on that boundary line are non-solutions. Whereas if we look at the graph of this, it has a solid boundary line to indicate that points like 7.2 comma 4 are solutions. And what is the graph of x is less than or equal to 7.2 going to look like? You got it. Same boundary line, but just on the points shaded towards the points that are less than that. Okay, now what if it was y is less than or equal to 4? Well, here x equals lines like this one have a vertical line. This has a vertical boundary line. So y equals something is going to be a horizontal boundary line. Let me turn these off. And so what do all the points that are shaded green have in common? They all have points like this one right here. It's going to be -2 comma -2, which means its y value is less than 4. How about over here? This looks like -10 comma 3-ish, and that 3, that y value, is less than -4. Okay, so we've covered these graphs. And by the way, when we have these graphs, the shape of this graph is called, or the shape made by this graph is called a half plane. This shape is called a half plane. Why is it called a half plane? Well, because if it didn't cut it in half, it would be a whole plane. For example, this is a half plane, and this is a half plane, and together, if I shade them both the same colors, it's the whole plane. It covers everything. And so when you just draw a dividing line right there at 7.2, it includes half of the plane, and the other half is non-solutions. And of course, planes extend infinitely in two directions, or in two dimensions, rather. Okay, let's close that down. Okay, now what about this? What if we have multiple inequalities? What's going to happen? Well, let's think about it for a second. This says 1 is less than or equal to y, which is less than or equal to 4. Can you think of a number that is that 1 is less than or equal to that number, which is also less than or equal to 4. Maybe a number like 3. 1 is less than or equal to 3, and 3 is less than or equal to 4. So 3 would be a solution to this. And this is y. So it doesn't matter what the x is, as long as the y is in between 1 and 3. And so y equals 1 is here, y equals 4 is here. And so basically any point in this strip with a boundary line of 1 and 4 will be a solution. And this is called a compound inequality. Turn that back on. All right, can you switch the boundary values? So for example, this says 1 is less than or equal to y, which is less than or equal to 4. Can you switch them and have 4 is less than or equal to y, which is less than or equal to 1? We know that this looks like that red strip. We wouldn't call that a half plane because it doesn't divide the plane in half. I don't know what you would call that. A horizontal strip. Horizontal, yeah. Now, what happens if we switch? Let's see. This is purple, but I don't see any purple. Let's look around. Nope, nothing under here. So, why aren't we seeing anything? Well, it's because if you think of a number that 4 is less than, think of a number that satisfies that part. 4 is less than or equal to y. So maybe that might be like 10. 4 is less than or equal to 10. Now, think about the other spot. Is 10 less than or equal to 1? No. And it's impossible for a number to be less than or equal to 1, but then for 4 to be less than that number. So that's why there is no graph here. There is no solution to this in compound inequality. So switching them did not work. However, what we could do is this. Notice we still have the 4 on the left, the 1 on the right, but what's different? This was a less than or equal to and less than or equal to, which matched these. However, this is greater than or equal to, and so this is going to work. Notice it looks exactly the same as that one. So why did it work? Well, because now there are values of y that are between 4 and 1. Let's see, this says 4 is greater than or equal to y. What numbers is 4 greater than or equal to? Maybe a number again like 3. 4 is greater than or equal to 3. And is 3 greater than or equal to 1? Yes. And it's basically everything here is flipped. The 4 went from the right side to the left side. The 1 went from the left to the right. And these less than or equal to inequalities became greater than or equal to inequalities. You could also do this as well. This, remember, did not work. 4 is less than or equal to y, which is less than or equal to 1. What you can do is you can graph them individually. 4 is less than or equal to y, looks like that. Again, 4 is less than or equal to what number? Numbers that are up here. Numbers like 5, 6, 7, 8. 4 is less than all those. And then y is less than or equal to 1 would be all these values. So while there is no solution that fits both of these in this compound inequality, compound meaning there's two, there is no number that satisfies both of these. If you wrote it like this, there are numbers that satisfy this one or this one. It's impossible, though, to be in this region and this region, but it could be in this region or this region.